Okay, welcome everybody to day 11. So Camille will be our TA guest lecturer for today on hydrogenation. But before doing that, I'll just go through a few administrative announcements and then quickly wrap up the problems of the day from the last worksheet, which I think naturally segue into the hydrogenation lecture anyway. So administrative announcements. One is office hours tomorrow, 11 to 12 with Nathan in the 5th floor conference room. That's a different location. Midterm then, as we said, will be Thursday, same time, same place as normal in this room. I'll break some bagels so that you can have brain food while you're working. The midterm is written now, and the one piece of general advice I would say is to use good test taking practices when you. It goes without saying, but I'll just remind you. There are points to be had throughout from the first question to the last question, and don't perseverate on something that you find tricky on question one. There should be enough time to get it done, but you need to work efficiently. So use good test taking practices. That's a reminder to do so. Okay, let's wrap up the day 10 problem of the day worksheet. I asked you to think through problem of the day number 1, which is to design a screen for this CSP3, CSP2 Negishi type coupling under nickel caps. This is a fairly real world situation. I can say this comes up commonly when consulting. If you were hired at a big pharma company, this is not outside the realm of possibility coming from this department that someone would say, we need to get this nickel Suzuki working, design a screen that's maximally informative. So let's think through, I want to jot this down on the board. We just keep this an open discussion, how you thought about designing your screen of 3 nickel precatalysts, 5 ligands to maximally, to interrogate this reaction as efficiently as possible, gain as much data as possible. So you might actually, one of the questions you might have in your mind is, why are we limited to this number? In principle, we could screen 10 precatalysts and 30 ligands, but actually, if you think about the statistics involved, this gets infeasible quite quickly, because at the same time, you're cross-screening against 10 solvents and 6 bases, and so the numbers here actually do matter. It starts to get difficult to do the post-reaction analysis when you get past like 10,000, on the order of 10,000 data points. Okay, so let's think this one through together. I guess I can, if there are any abbreviations that people throw out that are not common, and I'll jot these down and then erase it. So Wendy, what did you think here?
In terms of nickel?
Yeah, let's start us off in terms of nickel precatalysts.
I'm guessing nickel cod.
Okay, nickel cod. What else?
I would also choose a nickel 2 precatalyst.
Okay.
Nickel bromide clone.
Okay. Why do you choose nickel bromide lime as opposed to nickel bromide? Lime here is
maybe taking consideration its solubility in organisms.
okay, solubility, good. And lastly,
probably an entry point of some say one. I'm not sure how you can find a one.
okay.
That was something I would try. Probably one precatalyst developed by MJ Cole.
That's the one, the NHC. Okay, but that one you're going to be then stuck with NHC. That's one that we covered in class. Okay, any other ideas here? And I can use one of our pre-catalyst ones. There you go. Anything else? Anyone have? Someone must have had one different than this. Go up there. Alex, you put template. Any thoughts?
I would just say another nickel two.
Another nickel.
I didn't think of trying nickel one. I figured that was part of the team.
Let's try this.
Velocity.
Oxidative addition complex. 2. And why do we pick this one? Because it conveniently brings us to our chemist of the day from day 10. It's Sebastian Monfi, who together independently with a group of Abby Doyle popularized this pre-catalyst bearing the TMEDA. Now, this is not totally optimal. There's some disadvantage of this because you can't, the TMEDA never goes away and can pivot to catalysis, but it does undergo clean ligation with a number of different ligands in solution. And the original references for readings. I'll sneak over to my computer and jot it down. Seb is a chemist at Pfizer who did his training at Ottawa with Darren Fogg, postdoc with Paul Chiric, and has been one of the leaders in industry in base metal catalysis the last few years. All right, this is why I don't use chalk. Look at like my slant. It's terrible. Okay, and then ligands. What do we think?
Probably gonna start with
Triphenylphosphine, okay. Monodentate, triarylphosphine. What else?
yeah.
Identate, PPPF. Putting my skills to the test here. Yeah. What else?
Some sort of a NHC.
NHC, okay. Any if you like. Probably we'll put it in as the HCl salt. We're going to keep going. Okay. How about any other? Shenghua, what do you think? You've used some ligands in your day.
Like what? PP?
PP, great. Okay, some this nitrogen ligand. What else? One more to bring us home. Perfect. Okay, beautiful. I like the way this discussion went. And then bidentate and then tridentate, bisphosphonate, NHC. So the goal of the screen is to understand what ligand classes merit further investigation, and so this will cover quite a lot of space. That makes sense in terms of the thinking design. We want pre-catalysts that are soluble, that can cleanly ligate a number of different ligands. Ligands span a number of different structures, structural space, steric and electronic properties, and then we can iterate based on that. And this is not a, as I said, this is a fairly like real world practical example. So there are papers you'll find from BMS, they have Organometallics papers that's included in the readings for this week that is all about how to design screening sets for nickel catalysis. Okay, let's then this reference from the Pfizer team. This exact Suzuki was actually included. In case you are interested to read more. Okay, very good. Holiday number 2 is our segue to hydrogenation. This is asking us to think about a process that's closely related to hydrogenation, and one that we'll hear about today is isomerization. So first, we're considering this generic reaction where we're taking a beta substituted styrene. It's in the Z configuration, in the presence of a metal hydride. It's isomerizing to the E configuration. And we see that actually we're not using a metal hydride, we're using its close cousin, the metal deuteride. And we're getting a mixture of incorporation of deuterium into both potential. So the shape here. So let's consider the mechanism here. Dylan, what do you think? Mechanism for part A here that would explain formation of both of these products. Incorporation into both positions.
The metal coordinate the double bond first.
Okay, so what are we thinking here? Like this. I should draw this to the metal, not coordinate to the metal. Okay. So when metal hydrides coordinate to alkenes, what happens?
Migratory insertion, is that the right word?
Beautiful, yeah. And then which direction?
It looks like it's going to the beta position based on the product.
Based on this product.
Right, based on that. Oh, is that a D?
So the D
So
can go.
either way.
Okay, great. And here we're going to take some care to draw the relative stereochemistry, because this will be important. Or you say I can go either way. Repeating here what you're telling me. Okay, now what?
Reductive elimination to get to the product.
Well, what's going to happen eventually to regenerate the alkene? Reductive elimination won't give us an unsaturated product. Junta, what do we think? Okay. So we need to eventually, to get this product, we need to eliminate this beta hydrogen. To do that, we're going to need to rotate to get to a cis orientation, cissoid relationship. H then D here, and the same down below. I won't draw that just to finish the time. And then lastly, Junta.
Complete hydrolyte elimination.
Beta H elimination. We're going to lose the metal hydride here. Came in with the deuteride, we're losing the hydride. That's going to get us now to our product with the incorporation here. And if you follow the same sequence of events down here, product with the incorporation. Everybody clear on that? Classical sequence, hydrometallation, bond rotation, beta H elimination. Okay, so now we have a general mechanistic framework, and we need to now rationalize the relative extreme distributions in part B. So let's discuss this one as a class. Everybody have this? Okay. So let's first just consider the rhodium case. That's maybe the easiest, this top row. So help us rationalize this Madison. With rhodium, we have 100% D going to this position, 0% this position, 100% D going to this position, 0% going to this position. Steric, okay, and what's the other possibility? Okay.
That's just a more electron-rich site.
Aha, okay, I like this line of thinking. So let's just draw out our classical polarizations here. Figure out polarization of the substrate. And then that can report, and then that outcome here ends up reporting on the polarization of the metal deuteride. So we're saying to get regiochemical outcome we observe, we would need polarization like this. It's delta plus, this is delta minus, so that hydride here needs to be hydritic in character to get this. And then the polarity of the alkene is flipped in this case. That tracks with partial charge here. Very good. Madison? Okay, now the palladium case, more tricky. What do you think, Elin? What's going on here? Now we're seeing deviation.
Especially for the second case, the first, maybe the first one, the third one might be sigma, but for the second one specifically, we have the methoxy on the phenol, so we will have like a more electrophilic hydrogen remote to the that group, so we'll have like prominently at the second position.
So you're talking about the polarity of this starting material still. So this is now, it's like this, but it's kind of tamped down, right? Because you have this electron donation from resonance contribution here. So this is, if this is highly delta plus, highly delta minus, then this is tamped down, delta plus, delta minus, or even maybe neutral in character. Okay. So that's the substrate, but then what about the catalyst? Let's consider this extreme case here. Now with the palladium hydride catalyst, we see complete regio inversion. What is that reporting on? What is that telling us? How could we explain that? Ah, beautiful. Okay. So we've changed metals, and also we've changed ligands if you look into the details. And now we're changing regioselectivity, suggesting that the polarity of the metal hydride is different. We haven't changed the substrate, but we changed the nature of the metal hydride, the metal, and now we see different polarity. And so this illustrates, thank you, Elin, this illustrates an important principle of metal hydrides, that they can span a full spectrum of reactivity from being hydritic in character to protic in character. And actually, there's another axis here, because depending on the bond strength, as you'll know if you're in Ryan's group, or Dale's group, or Phil's group, also react like M dot plus H dot. These hydride bonds can be very weak, weaker than 40 kcal per mole, can be prone to hydrolysis and then participate in radical. So this is the very simple, one of the simplest organometallic species. The metal hydride has this complex suite of properties that can be tuned by the nature of the metal, nature of the ligand, the context. So for example, metal hydride reactivity, metal H reactivity, hydrogen atom reactivity manifests itself most commonly in first row moles because they have the weakest intrinsic bonds with organic fragments. I think that makes sense. And you can think about how you could change the electronic environments around the metal to bring about one mode of reactivity versus the other. So that's a key principle I want you to take away, and we'll see in hydrogenation and carbonylation how this manifests. And this overall approach of using these substrates with different polarization to report on metal hydride properties is called, named after our own Jin Kuan Yu from his time at Cambridge working with Joe Spencer. This is called the Spencer U test. Here, and then I'll turn things over to Camille. Any questions before I take a seat?
I'm just curious, so on the first case with palladium,
Yeah.
the proton-like metal hydride still goes to the place where it's partial positive on the substrate? What's
Did I misdraw this? It should be.
like the 8614 one?
Yeah, in this case, I guess that the observation that I want you to remember that this is a continuum. So let's say that palladium hydrides, they exhibit some protic behavior, but they're not the most strongly protic. And so the only observation I want you to take out of here is now you start to populate the other. So it's tipping. And then depending on, I mean, this is a quite juiced up substrate. So this one is really is asking to report on the protic reactivity, if that makes sense. We're just tipping over here, and then this is the case. We see, even in this case, we do see some of the minor. So these palladium hydrides are a little bit more amphiphilic. They're not extreme protic metal hydrides. And I realized I was standing off the screen for a bunch of that time, so it's going to be strange for the discussion, for the recording. Okay, take it away, Camille.
Okay, yeah, so I'm going to be talking about homogeneous hydrogenation and its talk. So I guess to start, just to make a few points on heterogeneous hydrogenation. These are complementary to homogeneous hydrogenation, particularly because they are extremely reactive. So they're going to hydrogenate a lot of functional groups, but they benefit from being able to be separated easily and reused because they're solid on a solid support. And on the other hand, what we'll be talking about today is homogeneous hydrogenation, which offers high stereo and regio control because of what we talked about last lecture, which is ligand ability to tune catalyst activity. So in terms of stereo control, this can be achieved through a directed hydrogenation in which the directing group exists on one face of the molecule and directs the hydrogenation to the same face, or via asymmetric hydrogenation in which the ligand sphere controls the stereochemistry of the hydrogenation. And then in the other case, regio control, which can also be a directed reaction, and also these catalysts that we'll talk about today exhibit a high amount of regio control, be it in terms of the amount of substitution on a double bond, the electronic character of the double bond, the type of double bond, meaning like a polarized double bond or a non-polarized double bond, etc. And this overall just gives the reactions high selectivity. And for these reasons, these types of reactions are used extremely commonly in industry. Another reason for this is that the main reagent is hydrogen gas, which is clean. So I think industry enjoys using gases because it's a reagent that just bubbles off after. So I'll start by talking about, for most of the lecture, by talking about achiral hydrogenation. This is mostly like a historical perspective, but I think a lot of the trends that we can learn from the early parts of achiral hydrogenation are still useful. So the first catalyst we'll talk about is the neutral rhodium catalyst, which is the one that I guess would be the most common historical example would be Wilkinson's catalyst. So can someone tell me what that looks like? And I'm not going to call on people, so you got to just shout. I know someone knows what it looks like. Okay, Elon, I am going to call on people. What? Oh, yeah.
Rhodium 1 triphosphate chloride.
Okay. Okay, and now, so yeah, that is the complex there, rhodium 1. So how could we make this?
Rhodium 3 trichloride.
Okay. And then, in this case, this is not a redox balance reaction. So what product has to form to balance it? Yeah, so we would eventually be forming the oxide because it's in the presence of an alcoholic solvent. So you would initially form the triphenylphosphine chloride, and then that could just oxidize in solution. Okay, so hydrogenations with Wilkinson's catalyst are typically run in benzene or other nonpolar solvents with a polar co-solvent, and they have extremely high functional group tolerance, especially for alkenes. But they also have a huge span of reactivity within the alkene series, so we can talk about that now. So here's, I started out the trend, so monosubstituted alkene is more reactive than 1,1 disubstituted, is more reactive than 1,2 disubstituted, which in the cis form is more reactive than the trans 1,2 disubstituted. Where do you all think we could place each of these two double bonds within this series based on the sterics and I guess, yeah, based on the sterics. So where would this one go?
This would be the least reactive.
Okay, good, yeah.
Dry substitute.
Perfect. Okay, so there we go. And then what about cyclohexene?
Cis disubstituted and the 1,1 disubstituted.
Okay. So why do you think it should go there?
Well, you have the ring there that's locking the double bond to a position that's going to be easier to accept hydrogen.
Okay. Yeah, so that's good thinking. It actually goes here because this ring configuration like pulls back this pulls back this constituent so much so that it's more reactive than even the monosubstituted. So going back to what Kiri was talking about, this catalyst does a cis hydrogenation. So the metal adds across the double bond in a cis fashion, and then the reductive elimination occurs from that same position that the metal went on to, and we'll go into more detail on the mechanism shortly. And along those same lines, if there is if we're running this reaction in the presence of D2 and H2, there will not be scrambling of the hydrogen and the deuterium. So each molecule will either have both hydrogen atoms or both deuterium atoms. Okay, so that concludes the quick discussion on Wilkinson's catalyst. And I'm going to go on to talk about cationic rhodium, which was pioneered by Osborne and Schrock. So cationic rhodium complexes appear in this form, which would be bidentate phosphine with some sort of diolefin ligand and a counter anion, which makes the whole thing cationic. So in the presence of hydrogen gas, this pre-catalyst forms the active catalyst. So does anyone have any idea how this gets on cycle from the pre-catalyst to the active form in the presence of hydrogen, because that's how we're running the reaction under hydrogen gas? I got called on for this question last year. Or 2 years ago. Okay, Cindy. Oh, she's not here. Oh, okay, Shinhua.
It's called gas hydrogenated off, right?
Okay, so how does that work?
Probably like some coordination slippage first to monodentate called and oxidative addition to dihydrogen and deliver hydrogen to one of the olefins and then deliver the second hydrogen molecule together.
Okay, so hydrogen oxidative addition, and then I'll just draw this like this. And then insertion of one hydrogen. Okay, so then we're gonna basically lose one of the double bonds, and then maybe coordinate solvent here, and then do the same process again to hydrogenate the second double bond, and then we would form the active catalyst, which is a extremely it's got only the phosphine on it and solvent. Okay, cool. So something to note here is that the hydride that forms here is extremely acidic. So this makes sense because it's a cationic complex, it's a charged complex. So you could, if you were to make the conjugate base, that would be a neutral complex. Normally things that are protonated and positively charged are acidic. So that means that these reactions are often run under acidic conditions in order to prevent decomposition of the catalyst. One other note that I'd like to make is these complexes often undergo the olefin first mechanism of hydrogenation, which means that once we form the active form, the next step will be coordination of an olefin followed by oxidative addition of hydrogen. And I'll go through this in more detail shortly, but I just wanted to note that while we're talking about it, because it is often the case, but not always the case, that if the complex, it comes with the olefin on it, like as the pre-catalyst form, it will often go through the olefin first mechanism. So that's like an easy rule of thumb. So you can maybe guess that the Wilkinson's catalyst, because it doesn't have the olefin on it, would go through the hydrogen first mechanism in which H2 coordinates and oxidatively adds prior to olefin coordination. Okay, so back to the fact that the rhodium is acidic when it's a cationic rhodium hydride. So we're going to talk about a slightly different catalyst system, which you could imagine forming in the presence of base with this cationic rhodium complex here. So we have in this intermediate rhodium dihydride cationic. If you were to deprotonate this, you would get to a monohydride complex that is neutral. So here's some sort of catalyst that's similar to that. It's tris triphenylphosphine rhodium carbonyl hydride. And so problem of the day number 2 asks you to Wilkinson's catalyst affects, which is this one over here, which is the tris-triphenylphosphine chloride, affects hydrogenation of terminal and internal olefins. In contrast, this complex is highly selective for hydrogenating terminal olefins exclusively. So the first question is to provide the coordination number, oxidation state, d-electron count, and overall electron count for this complex, and then to propose a reasonable catalytic cycle that accounts for your answer to A and predict one or more potential byproducts. Okay, so yep. Thank you. Okay. Christine, can you provide the coordination number, oxidation state, d-electron count, and overall electron count?
Coordination number is 5. This is rhodium. What's more? So that's
Do you agree? And number of electrons. Yeah. Okay, perfect. So now we need to propose a catalytic cycle that might have some byproducts associated with it. So I've started over here. So this is based on this being an 18 electron complex. We're going to first need to dissociate a phosphine to give ourselves an open coordination site to continue with catalysis. So what might happen first?
Coordinate the alkene.
Okay, so that is one option. Yep, so we can coordinate the double bond and form this. Thank you. Oh, it's not. Oh, and then, okay, now what happens? Yeah, do tell.
Regulatory insertion.
Okay, great. I'm gonna erase this stuff. Okay. Migratory insertions, we already have the hydrogen on there. So it makes sense that we are going to do migratory insertion RCO. Okay, cool. Now we have an open coordination site. So what could happen next? Okay, we could coordinate another olefin. Would that be a productive pathway? No. Okay. What else? Okay, great. So we're going to need to get another hydrogen atom on here. So we're going to want to do oxidative addition into H2, possibly preceded by just coordination of H2. So okay, great. And then lastly, what happens? Reductive elimination. Okay, and then we get back to the starting complex and we get product. Okay, so there are a couple deactivation pathways that could exist. So this product here is involves two different species. It involves hydrogen and the rhodium complex. Sometimes intramolecular reactions tend to be faster, even with high pressures of hydrogen. So what could you imagine happening with this complex here that might be a non-productive pathway? Okay, great. So you could do 1-1 insertion, and in fact, this complex is a known complex for hydroformylation. So if you were to do insert the CO and then you could then continue on, you would get the hydroformylation product. But in order to continue this catalytically, you would need CO present. So that is one potential byproduct. Okay, anything else that could happen here?
Beta hydrogen elimination.
Okay, good. So one note that the problem made is that this complex works really well for terminal olefins. If we had inserted the rhodium at this position, so if we, I guess if we have like a long, the reaction is drawn with a long chain intentionally, because if we had inserted the rhodium instead here and the hydrogen here, and then did beta hydride elimination, you could get the internal olefin, which would actually sequester the catalyst off cycle, because that, yeah. So then you would form a rhodium internal alkene, which is an off cycle pathway for this particular catalyst. Okay, so that is problem of the day number 2. Are there any questions? So all of this happens if you were to run Wilkinson's, or sorry, not Wilkinson's, the cationic rhodium, if you were to base or maybe not add a little bit of acid. And yeah, I forgot it. Okay, so that's that. So now continuing on with Crabtree's catalyst, which is the cationic iridium. Oh, I erased some of what I wrote. Okay. So Crabtree's catalyst is an extremely reactive catalyst because it it's really fast for hindered olefins, which means it could even hydrogenate tri-substituted, tetra-substituted olefins. So this is what it's useful for. And the reason it's so reactive is that it has a pyridine rather than a phosphine. So this is like an extremely labile ligand and makes this a really reactive catalyst. So it also, because it's cationic, and same with the cationic rhodium, is really great for directed hydrogenation because it has a high affinity for polar functional groups. And it relies on nonpolar solvents, and it's extremely selective for olefins. So these are some of its properties. One thing that was observed early on with this complex is that it was known to coordinate hydrogen, and this was observed through a color change. So in the presence of hydrogen, it would undergo oxidative addition and form a colorless solution. And a lot of the early literature on hydrogenation was studied extremely thoroughly, so the mechanisms are known with a lot of clarity. This complex was also studied a bunch, but has one of the more mechanistically complex processes. So just to demonstrate a few of its properties, I made this chart up here, which let's see. Okay, so Crabtree's catalyst up here, in the presence of DCM, the turnover frequency for 1-hexene is 6,400. For cyclohexene is 4,500, and for tetramethylethylene is 4,000. So, and this is at 0 degrees. So even with extremely hindered substrates that I will show won't work at all for most other pre-catalysts, this is extremely reactive. And then if we exchange one of the pyridines with a phosphine ligand, also at 0 degrees in DCM, it's still reactive for the hexene and the cyclohexene, but significantly less reactive turnover frequency for the tetrasubstituted olefin. And then using the COD diphosphine cationic iridium, but in the presence of a coordinating solvent, reactivity is pretty much completely shut down. So we only get 10 turnovers and 0 turnovers for the other 2. And then to demonstrate this with the cationic rhodium complex in DCM, it gives 4,000 turnovers for one hexene, 10 turnovers for cyclohexene, and no turnovers for the tetrasubstituted olefin. And then for Wilkinson's catalyst at 25 degrees in benzene and ether, it's giving 650 turnovers here and 700 turnovers here and 0 here. Okay, so I think that demonstrates pretty well the selectivities and properties of these catalysts that we've discussed so far. And so now going to problem of the day number 1 from the worksheet. Does this unclear to anyone? Get that right, including unclear. Okay, so problem of the day number 1 has an iridium complex. Oh, it shows Crabtree's iridium cationic complex with a tetrasubstituted olefin, and this tetrasubstituted olefin hydrogenation can give 5 or more possible products depending on the regiochemistry and the stereochemistry of the hydrogenation. So I'm giving you 1 minute to talk to your neighbor to predict which product will form and why. Does everyone have a worksheet? Yeah. Okay, Shaquan needs a worksheet. Anyone else? Yeah. No. Okay, raise your hand for A. Okay, raise your hand for B. C. Okay, we have 1 hand for C. D. E. Okay. Can someone who said A explain their thinking? There's a lot of you who thought about this and raise your hand for A. So that means people should be jumping out of their seats to explain. Okay, so the ketone is directing the catalyst to the top face, which means what for the methyl groups that are on the olefin? They're going to push down. Okay, so why do you think oxygen is directing? Just look at coordinates. Okay, so the oxygen and the ketone can coordinate to the cationic iridium and direct it to the double bond here. And we said that iridium has a high, cationic iridium has a high affinity for polar functional groups, for directivity. And then that will direct to the top face, and then causing the hydrogenation to occur from the top and causing the metals to be on the bottom. Okay, so this is true, and this would give you product A, but in theory, it could also give you products B or C, right? Depending, you've only discussed the initial coordination of the iridium. So you're saying that there's gonna be a cis hydrogenation. Okay, does anyone have any other thoughts? Everyone agrees? Okay, yep, so I agree too. This will give product A. And these complexes, I guess in terms of E, the Crabtree's catalyst is selective for olefins. And we'll see some complexes later that are selective for ketone reduction. Okay, so that concludes. Yeah.
When you coordinate the oxygen to the iridium, does it replace any of the ligands on it, or?
Yeah, that's a good question. So to reach the active catalyst, you would no longer have the cyclooctadiene on there, as we discussed. So it's likely that the PCY3 will remain on the complex. Okay, so. Oh, other way. Okay, so the next topic we'll discuss is ruthenium catalysis. So ruthenium catalysis are some of the most widely used for asymmetric hydrogenation. So one example of ruthenium, which looks similar to the other complexes we've discussed, is this one here. So this is okay. And so this is also selective for terminal over internal olefins, and it lacks a binding site for directed hydrogenation, which limits its use. Okay, and this area was pioneered by Naori. He specifically developed ruthenium binap, acetate, and the same one, but just with the dichloride. And so I'll talk more about Naori's work when we discuss asymmetric hydrogenation later on in the lecture. Okay, so this will just be come back to later. So now for directed hydrogenation, we already got a peek into it for problem of the day number 1. Yeah, I guess I kind of already hit all the points on this, just that it's mostly the cationic complexes, and that it's useful for both controlling stereochemistry, but also for controlling regiochemistry. Okay, so now I'm going to talk about the mechanism of these complexes, or these catalysts for hydrogenation. So one point I'd like to make is these, so like I said earlier, these have been studied extremely thoroughly in the literature and are known very well. So I guess just like talking a little bit about what we discussed last class in terms of figuring out a catalytic cycle in each elementary step within that. So the textbook makes a useful point, which I think is good to point out when we are discussing our first formalized catalytic cycles of the class, which is that in order to deduce the entire mechanism of a catalytic cycle, one needs to confirm the rate of every single step within that cycle to ensure that it does not act negatively upon the rate of the overall reaction. So, for example, in Wilkinson's catalyst, every single species that is observable spectroscopically is not on the catalytic cycle. So none of the species that are within the catalytic cycle have ever been observed during this reaction. And so it's important to actually use kinetics to deduce the cycle rather than just saying, oh, I observed this intermediate, therefore it's on the cycle. And something that I've always found useful to think about is that a catalytic cycle is like a wheel. So every part of the wheel must be moving at the exact same rate for that wheel to spin. It's actually the rate constant within each step that's changing. So if you were to add an off-cycle intermediate to a reaction, you would see that the rate is decreasing. And this is one way to determine whether the species that you think is the active catalyst is actually active. Okay, so now going back to this hydrogen first versus olefin first mechanism. So hydrogen first is exactly how it sounds, which is followed by Wilkinson's. And remember, this pre-catalyst has no olefin, so that's a hint that it's going to be the hydrogen first mechanism. So here we have LLL chloride. So this, what's the oxidation state of this? How many d electrons does it have? Okay. And what is its total electron count? Okay, cool. So in theory, we would think, oh yeah, awesome, this is catalytically active. We just throw it in, it's on cycle. This is not the case. So here's an example where you need to dig deeper to actually figure out what's going on. This is found to lose a ligand prior to entering the catalytic cycle. I don't think you'd be able to predict that, but it was shown mechanistically, minus L. So, and now we have our open coordination site. So this could also just be solvent, but we just draw the square because solvent isn't really a strongly coordinating ligand. Yeah.
Does like trans effect at all come into play here? Like would certain ligands be more likely to leave, or like does that matter at all in this part?
So the ligand in this case, if we're talking about Wilkinson's, they're all triphenylphosphine. And if the chloride were to leave, you would form a charged complex.
Yeah, I would just think like trans, like losing one trans to the chloride versus.
One of these. Oh,
Yeah.
yeah.
Two different.
But
I don't know if that like actually.
So I guess that might be more of effect for like ligand substitution, but in this case, we're simply losing a ligand. Would that be a fair way to look at it?
The position that you've drawn will be the least sterically, sorry, the least sterically encumbered. Would be the one with the strongest trans influence, so you could make an argument for either based on first principles. I think. Probably in your active species, you don't want the two triphenylphosphines to be cis, if that makes sense, if you can avoid it.
So then it might be more accurate to draw this. Okay.
I think we're steps you're going to talk about.
Right. Okay, so this is a hydrogen first mechanism. So then we'll coordinate H2. And then next coordinate olefin. Followed by migratory insertion into the double bond. and then reductive elimination to give back the active catalyst. So just the only thing I'll say here are two things, is that if the cationic rhodium has alkyl phosphine ligands that are electron donating, sufficiently electron donating, it can react by the hydrogen first mechanism. And second, if the olefin binds before oxidative addition of hydrogen, this can sequester the catalyst, especially for strongly bound olefins like ethylene, for example. So the next naturally will be the olefin first, which is followed by cationic rhodium. And we kind of already mentioned this, but I will just draw it anyway. So we already talked about how it can get activated to be coordinated by solvent. And then because these are often used with a directing group, I'm going to draw our olefin in a directed manner. And then followed by oxidative addition of hydrogen. Migratory insertion. Which can be trapped by a molecule of solvent. And then reductive elimination to give the hydrogenated alkene. Okay. Any questions?
So for the hydrogen first mechanism, why is a ligand dissociation took place at that position rather than the cis position to the carbon?
So that's what Madison was just asking. And I guess a steric argument would be that if these are phosphine ligands, you would want them to have loss of the phosphine between them.
So we do not consider the trans effect.
The argument is like you might like the one trans to the other phosphine might leave first, but then it rearranges to ester one because you want the bulky triphenol phosphine to be opposite to one another. It's like equating, I think.
Catalytic cycle, you also need to take into account what intermediate is fastest, not just which is formed fastest. That makes sense. Yeah. So sometimes in a cycle, we just draw one intermediate. In reality, you can form multiple isomers that just try to draw the productive one.
So now I'm going to be talking about a mechanism that has a generic mechanism for the hydrogenation of olefins and ketones that involves a metal ligand cooperation. So the hydrogen atom on the ligand and a hydrogen atom on the metal will both end up in the product. So this cycle is can come from L and M being bisphosphine, ruthenium hydride, arene, ruthenium, CP star, rhodium, and CP star, iridium, and then the supporting L will be N-tosyl, NH4O, and that'll make more sense in a second. So we're going to start by showing a metal hydride where we have an NL. So here's what L is, and then N is HR. So for this one, we're going to show the hydrogenation of ketones. I'm just going to draw this as acetone for simplicity. So the first step would be we have the hydrogen on the metal, and this can reduce from the carbonyl carbon position first to form a metal oxygen bond, and this here, and then we have an R, and then the protonolysis of the oxygen using the hydrogen that's on the ligand will give product, and this ligand bound, and then it's shown that this is now an anionic ligand. And coordination of hydrogen. So these cycles are thought to be, so the metal retains the same oxidation state the whole time. So rather than doing oxidative addition of the hydrogen, it just automatically, just like the hydrogen adds across what is kind of here drawn as a double bond. So the ways that this can be toggled between olefins and ketones is that if we're talking about ruthenium specifically, if it's ruthenium acetate, then it will be olefin hydrogenation, and if it's a ruthenium chloride dimer in the presence of base and alcohol, then this will perform ketone hydrogenation. So yeah, there's a lot of different mechanisms that can occur here, but this is just like a generic one showing that these like bifunctional ligands, they're not only acting as ligands, but they're acting as hydrogen atom sources. So this takes us to an important historical example, which of an outer sphere pathway, which is the Schwo catalyst. So the Schwo catalyst looks like this. The bridging hydride, so it's a dimeric complex. And it has a hydrogen, it's a metallohydride and a ligand-centered hydrogen. And in solution, this can readily dissociate to form two the rhodium hydride and the corresponding alcohol. And this hydrogen acceptor and this has been shown to racemize alcohols and carbonyl compounds or amines. And so this has been used in DKR. So this side can reduce a ketone or similar through a similar pathway as shown here. And on the other hand, the opposite partner can do the oxidation. So they can interchange between each other. So, and this bifunctional complex can also function for Niori complexes, which are of the type shown here. And these have also been used for asymmetric hydrogenation. So something that allows these to be specifically useful for ketones is that they are polarized well. So rather than, so I guess a lot of the, where both of the hydrogen atoms are centered on the metal, is that those hydrogen atoms are less polarized. So they're going to add to less polarized double bonds. But in this case, when we have a ligand-centered hydrogen atom, this is more polarized to add to the more polarized functional groups. So one keying element you can notice is that if it's a metal ligand bifunctional hydrogenation, then that's going to possibly favor things like ketones or amines or nitriles. So some other catalysts that I won't go into as much detail on include radical-based. So at the beginning of the lecture, Kiri talked about radical-based hydrogenation. So this is typically first row, metal radical, hydrogen radical, and then sigma bond metathesis can also enable hydrogenation. And then lastly, bimetallic hydrogenation, so meaning two different metals that are enabling hydrogenation. And the chemist of the day does work in the first row hydrogenation area. Does anyone know who he is?
For your presentation. But I forgot his name.
Do you remember what university he's at? Anyone else know? Okay, his name is Chang Liu, and he's at Tsinghua University. And the third problem of the day is related to his work, but I think we'll save a couple more minutes before we do that. Okay. So next, so basically the textbook goes into a ton of detail on asymmetric hydrogenation. And if you want to see every ligand under the sun and possibly its synthesis, you can refer to the textbook. But some early findings were that C2 chiral ligands would work quite well. So when this phosphine is triphenylphosphine or diphenylphosphine with this naphthalene backbone, which is C2 chiral. Oh, no, this way. C2 chiral, this can enable I can't figure out how to draw this. pH2. There we go. Okay, so this is binap. And there's also chiral at phosphine, which I think initially with asymmetric hydrogenation was kind of the focus, and maybe this has picked up more in recent times after the C2 kind of C2 chiral and other types of chiral ligands that weren't chiral at phosphine took over. But one of the example of that is here. So, and extensive lists of ligands, like I said, are in the textbook. And then just like one other class to mention is there's also veracenyl-based asymmetric ligands. So kind of referring back to problem of the day number, whatever number, the first one we talked about today from last time. If you were to be doing a screen for asymmetric hydrogenation, it might be useful to think about all the different cores that could be used. And I guess the reason that this
branch of the, I mean, probably that you have a triphosphate.
oh, sorry, this shouldn't be here at all. Oh yeah, there it is. Oh, you're right, it's symmetrical. Thank you. There we go. Good. Thank you. So within an industry, most chiral centers are made through asymmetric hydrogenation. So that's why this reaction is so important and why so much of the book is dedicated to it. And so just to give an example of that, in Novartis got FDA approval for a drug called sacubitril, which can be used to treat chronic heart failure. And one of the steps in their synthesis involves the asymmetric hydrogenation of an enone. So I thought this was an interesting reaction because the ligand looks so expensive. And they're doing this like on process scale. So I think, and it has 99:1 DR before crystallization. So the product here is so they're just forming the single stereocenter here, using 20 bar of hydrogen, ruthenium, p-cymene, is ethanol at 40 degrees Celsius, and the phosphine, which you can look up because I cannot draw it so large, it's called mandephos. So yeah, these reactions are extremely important in industry for the synthesis of chiral centers, and it seems like a lot of optimization probably went into this single step to identify this ligand and these sets of conditions. So that is all I'll talk about for asymmetric hydrogenation. And then there's another type of hydrogenation called transfer hydrogenation. Does anyone, can you raise your hand if you've heard of transfer hydrogenation? Okay, so transfer hydrogenation means taking a saturated molecule, for example, an alcohol, and oxidizing it, and taking the two hydrogen atoms from that oxidation and reducing or hydrogenating another molecule, such as this non-acetone ketone. To make. This. So I guess for a lot of us, it might make sense if you wanted to do a hydrogenation to do this type of hydrogenation, because you're not having to deal with an autoclave, high pressures of hydrogen. But in industry, like I said earlier, hydrogen is actually considered a really great reagent because it just bubbles off. But a lot of the transfer hydrogenation maybe could be considered more laboratory research-based preparative use. So I'll draw a cycle here rather than just showing that steam below. So in order to favor product here, this has to be run in solvent levels of the hydrogen atom donor. So one example is shown here. And then just coordinate it to ligand. So here's our substrate, and this will be hydrogenated. And then this, I guess, is another example of the metal ligand bifunctional catalysis, where we will then form these. No, we will form single. Oh yeah, single. So this is now anionic, and then here, and then to balance this cycle, the solvent, which is often an alcohol, in this case isopropanol, gets converted to acetone. So these are really nice too, because it's very easy to separate the byproducts. It's just a solvent that boils off. So an overall outlook for the field of homogeneous hydrogenation is base metal catalysis. So a lot of the historical examples involve expensive second and third row metals. And another outlook is arene and heteroarene hydrogenation. So I think we would still think, if we wanted to reduce benzene, you would think birch. Your first thought would probably never be homogeneous hydrogenation, but this is an opportunity for the field because of the selectivity that we've discussed. And then lastly, there are still areas within asymmetric hydrogenation that I think will continue on because of the importance in industry. So if we want to look at problem of the day number 3, this is an example of some of the frontiers in catalytic hydrogenation by our chemists at the lab. So the question asks you, Asymmetric heteroaryan hydrogenation with base metal catalyst remains challenging. Consider the asymmetric manganese catalyzed reduction of quinolines shown below. Explain the catalyst structure function relationship in terms of reaction mechanism. And I guess propose a synthesis of the chiral ligand. So the problem, I can draw it out. We have a quinoline and in the presence of a chiral manganese complex, base, solvent, and asymmetric hydrogenation of the heterocyclic portion of the quinoline first. So if you look at the three complexes on the right portion of the question, the first one is the one that is used in the reaction that has been drawn on the board. The second one is methylation of the backbone of the ligand, and then the third is methylation at the binding where the ligand binds to the metal at that secondary, now tertiary amine, and we see that that completely inhibits reactivity. So the first question is to explain the catalyst structure function relationship in terms of mechanism, and then possibly propose a synthesis. So I'll give you 1 minute to think about these.
What is the hydrogen source of this?
So I think that might be missing.
Just correct that.
Okay, so can someone explain why the yield goes from 98% to 32% and the EE goes from 97% to 60% when the backbone of the ligand is methylated? Who wants to answer? Annabelle? Do you know? Oh yeah, she's here. Okay.
On the backbone is also involved in the hydrogenation step.
Okay. So we're saying that this is involved in hydrogenation. How would you justify that in terms of a mechanism?
Carbon chain should be attached, not to the nitrogen.
Yeah.
So it's the upper.
Oh, this one's fine. Which one's?
And C. Right.
Oh, I see, here.
Decollate at that position and make the other nitrogen not coordinate to the manganese center somehow.
Okay, that is an interesting thought. So you're saying if we could, if this somehow gets deprotonated and it becomes an anionic ligand in the active form of the catalyst. Okay, so I don't think that makes complete sense because we're still seeing reactivity and EE here. So we're able to bind still and get enantioselectivity. I think another
Acceptor. Sorry, acceptor of hydride, since we don't have, for example,
We're doing a ligand cooperation and we don't have something like acid
we don't have something like
or isopropanol.
okay. So so this is not like a transfer hydrogenation per se. I think if we think about this more in turn, I think this needs to be thought of also at the same time as we're thinking about the last complex, which is that reactivity is completely shut down when there's methylation at this position. So I guess to guide the conversation a little bit, there's with enantioselectivity, we have sterics as a huge factor. So maybe you could say sterics here are causing this complex to bind more poorly with the wrong geometry, or sterics here, when you methylate here, are preventing bonding completely. Or another way to think about it is if I draw, so if we were to draw, so I think Alex was on the right, track when, so if there's this hydrogen, so this is the portion that is so here's the substrate. It's getting this double bond broken. So we do need to get hydrogen on the manganese to enter the catalytically active form. I'm just gonna okay, so this portion of the ligand here can interact. Oh, sorry. Okay, so here's the ligand, here's the substrate. So we're seeing that there, with this portion of the ligand, it's actually it's adding hydrogen directly to the substrate. So when you remove that hydrogen atom, there's no ability to reduce the substrate. And I think that for this position here, there's more of a steric argument to be made because we can see that there's this pi, like some sort of pi stacking effect possibly, which is hard to draw on the board. But when this is methylated, that pi stacking is diminished severely, which would affect the enantioselectivity and the yield. And you can look at the paper, which we will send out.